for the invitation for giving this talk. Thank you. I would like to talk something about sonochemical carbon dioxide reduction over copper-based catalyst. I want to say this work has been done at the University of Oxford, supervised by Dr. James Kwong. So just want to show you why we want to do CO2 reduction. One of the reasons that we want to transfer to a net zero landscape by 2050. Even in the UK, we want to reach the carbon neutrality, but it's quite challenging. One solution is that we can reduce the emission of CO2. Another way is that we can convert CO2 into very useful chemicals and even fuels. But you can see from this figure, CO2 reduction pathways is very complex. You can see it involves complex processes leading to the formation of various products. From here, this figure, you can see so many routes to produce different products. And also, if we want to produce a specific product, this will be very, very challenging because the selectivity is very, very low. For example, if you want to produce a carbon-2 product, you must use the carbon-carbon coupling to form the carbon double bonds. Here you can see this CO. You can see if you want to produce ethanol, this will be a very, very long way. So any process can be disturbed. So that's why if you want to improve high selectivity of carbon-2 products, multi-carbon products, the selectivity is very, very low. So it's very challenging. So this is what we want to do right now. As you have heard a lot about electrochemical CO2 reduction, thermochemical CO2 reduction, photochemical CO2 reduction, but not too much have been done about sonochemical CO2 reduction. So here I want to introduce to you what is the sonochemical CO2 reduction and what is the acoustic cavitation. Actually, for sonochemical CO2 reduction, we want to use ultrasound to produce bubbles. The bubbles will gas that will collapse to form very, very hot temperature and very hot conditions. These hot conditions, very hot temperature, they will produce various of radicals. These radicals will help reduce CO2. So that's why we can produce so many products. And why we want to use sonochemistry? Because sonochemistry, you can see the electricity driven, it's called green. And also it has really good operational simplicity, and also it's high safety and environmentally green. Just want to show you a photo about the sonoluminescence. So this is you can see the video. The bubble is collapsed. Suddenly it will form a sonoluminescence. It's like a very, very hot temperature. So that's why from now it's like a thermochemistry to produce such radicals to help you reduce the CO2. As you know so many about the and the thermochemistry, but not chemistry, electro and the thermochemistry. But how thermochemistry CO2 reduction proceeds over catalyst surface, and what are the products? This area has been, not there really over exported. So that's why what we want to do is that we want to check the products and want to know the mechanism. Here I'll give you some photos about how I do the sonochemical CO2 reduction. From here you can see this is the sonochemical CO2 chemical reduction reactor. This is the reactor. We put our catalyst in a vial, then we'll put a syringe here to draw the gaseous products. Then we analyze to use the NMR. For each standard reaction, we let it run like a sonicator for 20 minutes. Then we collect the liquid and the gaseous products, we analyze them. And because we want to combine with electrochemistry and inspired by the electrochemistry parameters, so many people already investigated. So we want to check what are the products and efficiency in the presence of potassium bicarbonate. And also we want to change the atmosphere. We want to know the selectivity and how much products we can convert. And also we want to understand more in depth. We want to understand if we add some other cations, what are the products and how it will affect the sonochemical CO2 reduction. This is the background. Then we want to do some real sonochemical CO2 reduction. Firstly, we synthesized some surface roughened copper oxide nanoparticles. You can see the surface roughness has been confirmed by both SEM and TM images. Why we want to use the surface roughened catalyst? Because during the cavitation, we can generate loads of radicals, and these cavities can help you capture such radicals. Then because you capture loads of radicals, that will help you to reduce CO2 to produce so many different products. And give you some very basic results. Firstly, you can see from the axis, we firstly check the CO2 saturated solution, use water, different concentrations of potassium bicarbonate, and the y-axis are the products. Here you can see we can only produce hydrogen and CO in the liquid products. And we found that if we don't use a catalyst, there's no products because the cavitation is very tiny, very weak, so no CO2 can be converted. And we found that if we use the 0.1 mole CO2 saturated potassium bicarbonate, we can use the largest amount of CO. So this is the best condition. Then we checked so many conditions regarding 0.1 mole potassium bicarbonate. For example, we changed the atmosphere, use CO2 argon atmosphere, because argon is very, very good to cavitation. So if you add argon, the cavitation phenomenon is very, very strong. So that's why it produces loads amount of CO. So this is really good. Then later, we want to know, because the catalyst, the activity loss and stability is always an unavoidable problem. So we want to know whether after sonochemical CO2 reduction, the morphology will be changed, and whether this will affect the CO2 reduction, whether it's positive or negative. You can see from the SEM images after CO2 reduction in different reaction conditions. We found that in the inert atmosphere saturated water, even potassium bicarbonate, you can see the morphology are well maintained. So that's why we guess that because the morphology has been maintained, so that's why it can give you really, really high CO2 to CO conversion. But from here, you can see if you use CO2 saturated water and the potassium bicarbonate, this morphology has been damaged. Such a deformed morphology, we think maybe not very good to induce cavitation. So that's why the CO2 reduction performance will be inferior. So to confirm this, we did some kinetics studies. You can see it's very easy to know that gases will accumulate as function of time. You can see these black lines. But if you change it to the production rate, you can see the longer term, the production rate will be slowing down. So we think maybe the catalyst has been deformed too much. So that's why the CO2 reduction performance is not that good anymore. So to confirm this, we did the ex situ SEM and TM images. You can see the longer cavitation, the morphology will deform very seriously. So this results just support a previous assumption that deformed catalyst is not very good for CO2 reduction. Later we want to know more, so we will change the ionize. We think maybe we want to improve the CO2 to CO conversion. So we change the potassium acetate, potassium chloride, even the high concentration of potassium bicarbonate. We found that this catalyst can totally deform our copper oxide. So that's why the CO2 to CO conversion performance is not very good. But this morphology, well-maintained catalyst, can give you really, really good CO2 to CO performance. And so that's why it's also further supported our previous results. Deformed catalyst is not very good. So we try to avoid such situations. And The important thing is that you can see check the CO and hydrogen ratio. This ratio is very good because it's a very important ratio for the syngas. So this is a very useful reaction. You can use different anions or different concentrations of potassium carbonate. You can change the ratio between hydrogen and CO for different chemical synthesis. Then later we want to know more about copper oxide because we want to produce more multi-carbon products, but previously only can produce CO. So we try to synthesize more different catalysts with different morphologies and different species. For example, the cubic copper oxide and even the cold shell cube and this sulfur-doped copper oxide cage and the deformed nanoshape morphology. And this has been confirmed by the XRD pattern. So we want to know what are the products. Then we further confirm the morphology by the TM. You can see here is the cage and here is the nanoshape morphology, very, very clear. And we did some sonochemical CO2 reduction in CO2 saturated water. We found that the original one, unmodified copper oxide cube, is the best catalyst. And we want to know why. And we found that after the sonochemical CO2 reduction, the catalyst has been deformed significantly, especially the cage. You can see some more like totally deformed. So that's why the performance or everything are not very good. They just further supported our previous results. So then we want to focus on these two optimal catalysts. We want to understand more situations. We want to know what's going on with such a catalyst. Maybe we can optimize such a result to produce more CO. Here you can see we changed the different concentrations. We found that the water, for such a batch of catalysts, water is the best solvent to do the sonochemical CO2 reduction. And you can see after the reaction, the morphology changes significantly. And also, if you use argon still give you the best performance because the cavitation is very, very strong. But if you use 5% CO2 and nitrogen, this situation has been totally changed because we can only produce hydrogen. There's no CO. So I think this catalyst, this reaction is very important. In future, if you suddenly don't want to produce CO, you can just change your atmosphere to nitrogen atmosphere. They will only produce hydrogen. So this is very interesting. And while this performance is very good, you can check from the morphology. After sonochemical CO2 reduction, it's just the surface changed a little bit, but the morphology is well maintained. So that's why the just want to say, totally support the previous results. You need to keep your morphology. Then your catalyst performance will be very, very good. So we also want to know, for the results, we also repeated the kinetics. You can see the longer time, the production rate will be reduced because of the dramatically deformed morphologies. It just totally, support the previous results. And from now, I just want to show you some sonochemical CO2 reduction, what I did at Oxford University. For this project, we really want to do is the sono-electrochemical CO2 reduction. So here I want to introduce you some electrochemical CO2 reduction. Sorry, I forgot to change the title. Here is some electrochemical CO2 reduction of still these 4 catalysts. You can see, sorry. If we use a carbon paper, there's almost no current density. And if we use argon saturated 0.1 mole potassium bicarbonate, you can see the dot lines. The current density is very, very lower. It means there's almost no CO2 reduction. It's a hydrogen HER, hydrogen evolution reaction. Here you can see if the dot lines, if you use the CO2 saturated solution, the current density is very, very high. And you can see the starts to do CO2 reduction at a very, very lower potential. So it means it starts to do the CO2 reduction. And I will give you some results. This is the results I tested during the sonochemical CO2 reduction. You can see we can only detect like 3 gases products: hydrogen, CO, methane, and the only liquid products we can protect for now is formate. Unfortunately, we didn't produce any carbon-2 products. And why you see you only produce formate? Because we use NMR, and we let this how to say, the reaction, electrochemical reaction, working at the most optimal potential for like 1 hour. You can see, let it run 1 hour, and we detect the liquid products. We only can detect the peak of formate. So that's why we can only produce formate as the liquid products. So just to give you a summarize that this catalyst, this copper sulfur, copper 7 sulfur 4, copper oxide cube can give you the best selectivity to produce formate. And also the current density is quite higher at the optimal potential. So later we just focus on the on using this catalyst to do more research. Give you a very quick results. We choose to use a different concentrations of potassium bicarbonate. You can see because you can see if you use a high concentration of potassium carbonate, the current density very higher because it will give you a faster charge transfer and a lower resistance. So that's why the current density is pretty higher. And also another thing, we want to do different concentrations because we want to optimize whether we can further improve the selectivity towards the production of formate. We found that we did find it. We found that this 0.2 mol potassium bicarbonate can give you relatively slightly improved selectivity, but it's also very, very exciting because previously I really wanted to improve this to like 90% because this is more economically feasible or beneficial. But unfortunately, I failed. And you can see the 0.1 mol is the best to give you the highest selectivity to produce formate. And later, we will use this concentration to check its stability, whether it's a long run and the selectivity will maintain or not, because stability is a very important parameter to assess your catalyst. And another reason I want to do different concentration of potassium bicarbonate, because we want to know formate. If you want to form formate, either it will source photons from water, or it will source photons from bicarbonate. We want to know which one is dominated, and we plotted the log partial current density of formate and also the different concentrations of potassium bicarbonate. We found that they show really, really high cursor one order dependence. You can see the coefficient all coefficients all above 0.9. So this is really, really good for the one order dependence. So it confirms that the protons are sourced from potassium bicarbonate instead of water. This is just a very basic sonochemical CO2 reduction and electrochemical CO2 reduction update at the Oxford University and Manchester Metropolitan University. And unfortunately, copper-based catalysts, no matter how you modify the morphology or change the compositions, only in sonochemistry and electrochemistry, they can only yield carbon-1 dominated products. But it's very good. For us, it's very good because in sonochemical CO2 reduction, we produce a lot of CO. CO is a very important intermediate to be coupled to form multi-carbon products. So the first thing that we want to unravel the sonochemical CO2 reduction mechanism. And the next thing we want to forward to coupling sonochemistry with electrochemistry. We want to produce a more multi-carbon products. And this technology, we want to use the sono-electrochemical CO2 reduction. This is our next step. And to give you very, very initial results, what I did at Oxford University, this is like a copper form, because during the cavitation, we don't want to lose our powder catalysts. We use a copper form as an initial try. So this is the original copper form. Then we use a potassium bicarbonate to modify the copper form and use a phosphoric acid to modify our copper form. Then I built this open cell to do this sono-electrochemical CO2 reduction. You can see the bubbling. This is the cavitation, and this is the opening structure, opening cell. This is the reference electrode, counter electrode, and everything is here. And this is an electro workstation. I can record the LSV to check whether this is good for sono-electrochemical CO2 reduction. And here you can see the screen, the very strong cavitation phenomena. It means it's successful. It's really, really good for sono-electrochemical CO2 reduction. And here you can record some parameters. And also here's a very simple picture to show you how I built this open cell for CO2 reduction. Later, I will try to make this airtight to do the edge cell for the sonochemical CO2 reduction. I will present study results maybe next time if you get the invitation. And thank you. This I would like to thank the UK Catalysis Hub to support this project, which is very, very good. And my supervisors, for example, Laurie King, he's doing the electrochemistry, and Dr. James Kawan, he's doing the sonochemistry. Yeah, thank you very much. This is what I want to say.
Thank you. The talk is open for the discussion.
That was a very interesting talk, thank you. I'm just wondering if you've done any kind of characterization of the oxidation state of copper. So for instance, any XPS or XOUT or anything to look at whether the oxidation state of copper changes, for instance, does it become copper 0 or copper 2+, or does it stay as copper +1?
Yeah, we did some XPS because the XPS is the most easiest way to distinguish the copper species and the ratios between them. Unfortunately, our XPS in MMU suddenly broke. But for the sonochemistry, we categorize them before. There's not too much differences. We just see the morphology change. At first, I thought maybe they may form some copper 0 or maybe copper 2+. But I did the XPS, did analysis. Even the peak position not shifted too much, and the composition are roughly keeping identical. So that's why I think I will redo the XPS to make sure whether it's just the morphology change, nothing about the valence states.
Thank you very much. On that same topic, so do I understand correctly that when you put your cuprous oxide powder in the vial, it's an electrical isolation during the experiment when you are reducing the CO2?
Oh, you in electrochemical? In
electrical isolation, you don't apply a potential or a voltage.
Applied. Actually, this will be reduced. Actually, previously we want to stabilize the copper species. We want to see whether it's stable because we will always give it negative potential. Previously, we need to do LSV to do several times to make it stable.
But could you go back to the picture you showed where you had the syringe sticking out of the experiment? So
you mean sonochemical or here?
Back. Yeah, so that's what you just showed. So in this experiment, did you apply any potential?
No, this is just sonochemistry. Just put it here. Nothing. They will do the cavitation.
And in this system, you measured CO2 reduction.
This is a sonochemical CO2 reduction. Yeah, and another one is electrochemical CO2.
Question about this one. So you load your cuprous oxide particles in there, right? You put in your potassium carbonate solution, you bubble various gases, and you see the reduction of CO2 and the reduction of water. Yes?
Yes.
But if this is an electrical isolation, you must then have a corresponding oxidation process, maintaining the reduction process, because the net current has to be 0. So something has to be oxidizing. What is oxidizing?
For this, it's like more like a thermal chemical CO2 reduction. So we will not apply any current here. No
But
electron.
you're measuring the reduction of CO2, so you're saying you're
Yeah.
reducing CO2. If you're reducing CO2, the electrons are being used up. Where do those electrons come from? So something has to be oxidizing at the same time as CO2 is being reduced. And I'm just wondering whether your cuprous oxide has to be oxidizing
Oh,
to
yeah,
maintain
yeah,
the
yeah.
reduction, and hence that morphology changes as a result of corrosion, which is basically inevitable. So I'm
Yeah, yeah.
wondering.
Yeah,
So,
yeah, we want to do XRD, and I just answered that question. We did XPS. We found that there's no, just the morphology changes. There's still no reduction of the copper oxide or something.
has
So
to be oxidizing, I think.
yeah, I think it should be, yeah, because, but I don't know why I did the XPS, I analyzed the data, almost roughly identical. Yeah,
But it's worth checking, because if the
Yeah.
system is an electrical isolation, something has to be oxidizing, which means that your catalyst is also consumable. If you're operating your cuprous oxide as a cathode, then you're saving it from oxidation, and then reduction becomes your problem. So you're dealing with different processes happening on your surface, which is separate in the electrochemical and non-electrochemical subset.
I think we'll discuss later.
yeah. Thank you. I'll talk with you more.
It's very
Yeah.
interesting talk. And also wondering about oxidation states. It's very well known that cuprous oxide is, I think, oxidized to or reduces to metallic state and transfers to cuprous. But it's very interesting talk. Thank you very much.